came up through the chat box. So I think, Jeannette, we'll start with you. You've seen there were many questions. The first, there were a set of questions about the reward for the outer loop and the inner loop. Yeah.
Yeah, that's good. I must have not explained this very well. So the outer loop gets as a reward how basically the reward, the maximum reward that the inner loop got. So basically, the faster the inner loop learns, the higher the reward for the outer loop. I hope this explains this question.
Yes, if there is a need to follow up, then you can ask the question live. So there is another question regarding the fixture. So can the fixture placing policy handle uncertainty, such as on variation of the task to be learned by the inner policy? Yeah, and there is a complementary question about the fixture. Have you considered a mechanism to find a curriculum to either way to support from the fixture to allow the inner loop to function independently?
Yeah. Exactly. So that's a very good point. I have not talked about that part at all. I'm just going to talk about the last question right now. How you actually remove the fixture then, right? Because the training wheels, when you learn bicycles, at some point you want to get rid of them. And exactly that is what we're exploring as well. So the policy that is learned with the fixture doesn't just work if you remove the fixture. So what we do is actually explaining a curriculum approach of removing this fixture again, while keeping a virtual potential field instead of the fixture, to then still execute that same policy, or actually refining it. So we do remove the fixture, we leave a potential force field there that is shaped like the physical fixture, and then refine the policy based on that. So that was kind of more to answer also for us the question if we can remove these scaffolds again. But I think it opens interesting new direction on saying like, okay, maybe I don't need a physical fixture. Maybe I can just place arbitrarily shaped force fields and explore with these to find or to better scaffold actually virtually. So we haven't worked on this yet, but that would be an interesting follow-up direction. And I think, sorry, the uncertainty, we have not systematically explored this, but because there is a physical fixtures that actually prevents these particular action space, I think it would be pretty robust against uncertainty from the inner loop. But that's a hypothesis, and we haven't really systematically tested this.
Okay, and just the last one, I'm combining here 3 different questions. How long does it take for training, and how much does it generalize with an underlying question of transfer learning?
Right. So actually, I'm gonna start with the last question again. We have actually trained everything in simulation, and then just replayed it on the real world. And also we just replayed in the real world with different pegs. So it was actually very surprising to us as well how well it generalized from sim to real. And we believe that the reason for this is that there are actually physical constraints in the first place that constrain the action space. And also we use the depth image as input, and depth images always generalize much better between sim and real compared to RGB images, for example. So about the training time, I'm really sorry, I don't know right now. I would need to look it up in the paper. And
that is fine. Yeah. You can also follow up by chat. I think it's good if you now take the time later on to answer some of the other questions by chat to everybody. If possible, try to copy everyone so that everybody can also benefit from these answers.
Sure.
Okay, thanks a lot.
Answer in the chat, right?
I'm sorry? Yes.
I will answer in the chat? Okay.
Yes, please,
sure.
in the chat, yes.
Okay.
All right, turning to Dagmar, we have a few questions. So what are your expectations regarding the change of the behavior for the exploration of the solution space if the motor task requires reaching to or maintaining an unstable state?
Ooh.
That was a long one.
So how to reach an unstable state? I think one aspect of learning a task is to modify the entire limb object system to one that maybe transition from an unstable to a stable state, if that is possible. The other somewhat abstract way of answering this is to, again, resort to the recognition that humans are very slow in their feedback control as well as very noisy, meaning they are actually much worse than robotic manipulators in these two aspects. So in order to achieve unstable or precision tasks, they have to modify the task to make it predictable such that one does not rely on slow feedback control, and stable to allow for the ever-present noise. So that's what I can say in this very high-level way. And I should say that some of that we have addressed in this other task where I just made a plug, which is more difficult. And in fact, currently, we're also looking at how to manipulate a web in order to make the task even more challenging and less possible to control with feedback-based error corrections, but rather to modify the object to actually make it predictable and stable in the end.
Yeah. And we have a somewhat complementary question. What makes some tasks easier to learn?
Ooh. I am also a great believer in exploiting passive dynamics of objects. So tasks that allow you to then make use of passive properties of the task, I think is what ultimately makes human performance better, which is consistent with a very old concept of how motor learning happens, namely from an active cognitive stage to an automatic stage, which I believe we had one spotlight, where the control of the task and the object is very kind of low level in the nervous system. There's no conscious control anymore. And the way I interpret this is that the human has learned to let the passive dynamics of the object play a very important role in achieving the task. But these are very tough questions. I mean, if I could really answer them, I would be at a different place.
Excellent. But we have more time for a longer discussion at the very end. Now, Andrea Del Vella has a question that he tells me will also lead as an introduction to his talk, so it's a perfect timing. Andrea, do you want to ask it live? And then
yes, please. So, Dagmar, you showed nicely how both in the dynamic stability task and in the exploitation of the solution manifold, people learn. But I wonder how much different participants, different individuals differ, and how much you think we can actually learn additional insight from looking at the inter-individual differences.
Yeah, so let me maybe rather refer you to the Skittles task, where you could see how we look at ball releases in this solution space. Their inter-individual differences are very visible. So we have typically this nonlinear solution manifold, and where subjects, individuals end up can be actually at very different places. What our work has focused on is to find, well, the invariances in what they achieve as well as how they achieve it. And that was this tolerance noise covariation approach, where again, there are differences, but the way and the sequence of how they utilize these ways of, call it manipulating their releases in the execution result space, is actually, again, relatively invariant. So unlike you, who has focused now in a number of studies on interindividual differences, I have tried to recognize them, but seek the invariances and leave the work for the individuals, for you.
Excellent. So let's